Thank you. So initially I was planning to use this third lecture to talk about the interacting case and explain what goes through in the interacting case compared to what I said last time. And then especially I was planning to discuss in some detail the calculation of these amplitudes that appear in the expansion of the operators in terms of the operators of the field theory, which was Fabian's question on Monday. But Filippo discouraged me and said that it was perhaps not the best idea to start talking about beta ansatz today, last day of the school. So, and of course he's right. So I will talk about something else, something less, hopefully a bit less technical, although it will still be quite technical. So this will be about entanglement. So entanglement growth after it's a domain will quench. And so what's a domain will quench? It's basically a special case of what Bruno was, of the setup that Bruno was discussing. So we are interested in a lattice with particles, so free fermions hopping on the lattice. And what's particular about this setup is that we are going to imagine that the initial state is a state where all the fermions, this is direction x, all the fermions on the negative on the negative axis. So for x negative, all the sites are occupied by a fermion initially, and on the right they're all empty. Then we will evolve the state with the Hamiltonian. The Hamiltonian the Hamiltonian will just be the this Hamiltonian just with pure hopping. This is the Hamiltonian of the XX chain after Jordan-Wigner transformation. And okay, so what happens when you evolve your state with this Hamiltonian is that particles start to hop. Of course, they hop only by one side. But so after some time, so if this is time, so at later time, particles have hopped, and so you have some particles here, say. So the density of particles on the left is still 1. Density of particle on the right is still 0. But in the middle you have a non-trivial density profile. And here, inside here, you get some complicated superposition of many possible configurations, and you can calculate you can calculate various correlation functions, but you can also be interested in how the entanglement entropy grows between a point here, so between a subsystem A and subsystem B. So initially this is 0 because there is no entanglement between here and here, but as time increases, this becomes non-zero, and so you can be interested in the growth of this of the entanglement entropy. And so the result I want to arrive at the end of the lecture is this formula. So you can derive an exact formula for this particular problem from from the free boson conformal field theory in some inhomogeneous situation. Here you see that something is going to be inhomogeneous. So you can adapt what we have discussed to get the entanglement entropy in this form. It's log t 1 minus x squared over t squared to the 3/2. And yeah, so I want to arrive at this. So I mean, this is a very particular setup. It's a very particular problem, very particular quantity. So you might ask, why should we be interested in that? I'm going to use it as a it's going to be an opportunity to introduce a few nice techniques and nice results from conformal field theory. Alpha is the Rayleigh index, and I'm going to discuss this. I'm going to introduce properly Rayleigh entropies now. Okay, any questions so far? That was just the introduction. Okay, so we are going to go. So entanglement entropy or entropies, and by that I mean Rayleigh entropies. So who is familiar with Rayleigh entropies or entanglement entropies? Okay, well, I mean nowadays it's a fashionable topic. So definition and swap. So swap operator. So imagine that we have a state that lives in a Hilbert space, and we have a certain bipartition for this Hilbert space. So imagine 2 spins or something like that, or a large spin chain that you cut into 2 parts. And so if you want to write this state as a sum of states that live in part A and part B, in general you have to write something like this. So where here you can choose these sets, psi I A and psi I B, so as orthonormal sets. Orthonormal sets. So the inner product between 2 of those with different indices is 0. And so this is the Schmidt decomposition. Schmidt decomposition. And we are going to work with normalized states, so that sum over I is the norm of psi is 1. Okay, and now the Rayleigh entropy. So these lambdas are positive coefficients. Their sum is 1, and so you may view them as a probability distribution. And then you can look at the entropy of that distribution. So the Rayleigh entropy is defined as S alpha is 1 over 1 minus alpha log sum over I. This n typically can be very large. It's usually it can be as large as the Hilbert space dimension of A and B. Okay, so that's the definition. If you take alpha to 1, it gives the standard entropy, von Neumann entropy. And now there's a trick that allows to write Renyi entropies, or more precisely this part here, as an expectation value if alpha is an integer larger than 2. So if alpha is integer larger than 2, then you can write this here as the expectation value in a system with several copies of your state. So here alpha copies. Of an operator that I'm also going to call S. Okay, let me put this S. SA. And also here alpha copies. And what does this operator S does? So S is for swap. Is the swap operator. And the swap operator is defined as follows. So if I have some state that leaves some product state for the alpha different copies, then the swap operator acts as a cyclic permutation on them. So it replaces S1 by S2, S2 by S3, and so on, up to S alpha, and then it puts S1 in the end. Okay? So, and I'm claiming that this is true here. So, I mean, if you've seen this, I guess it's clear. If you have never seen this, it might be little bit surprising the first time. So who thinks this is clear? Okay, just okay. So just the experts of entanglement entropies. But okay, so let me then briefly explain why this is the case. Well, I can write here. Okay, so let me do it really explicitly, but just for alpha equals 2. Then if you want to do it more generally, you can do it as an exercise. Okay, so I mean, there are more or less elegant ways of doing it, but let's do it in the most possible naive way. So, okay, so we have to write. So first we write one of the two psi's with the Schmidt in the form of the Schmidt decomposition. So this is the first psi. Okay. Then we need a second one. Then we have the swap operator, and then we need two other states. Okay. So. I4, This is a B. Okay, this is just so far just a definition. Then how does the swap operators act? So the swap exchanges the two states, but only in part A. In part B, it acts as the identity. So if you want, it acts. Sorry. Yeah, sorry, I didn't say that. Okay, this is why there's an A here. So it exchanges these states here only in part A. Okay, so if it does this on part A, and on part B it doesn't do anything. It's just the identity. So if you want, you can think. Yeah, okay. So think of this as an operator acting on A, and then here we have S tensor identity acting on B. Okay, tensor identity on B. Right. And so the swap exchanges these two. So it's as if it was exchanging the two indices I3 and I4. So here I have an I4, and here I have an I3. And then I can erase this. And then I need to contract the different states. So this one here, I have to take the overlap with this one. Sorry, this one here with this one here, and so on. And so then you can easily convince yourself that, so that you have a sum which involves the root of lambda of 4 of the lambdas with 4 different indices. But then you get a bunch of inner products like that, and because the states are okay, so I'm not going to do it completely. So there are four inner products here that you can write, and all of those give Kronecker deltas. And so in the end, this just tells you that all the coefficients have to be equal, and so you arrive at sum over lambda I squared, which is indeed sum of lambda I to the alpha for alpha equals 2. Okay. All right. And now we are going to go to field theory. So we want to learn how to calculate this in field theory, especially in conformal field theory. Any questions so far? So now I'm going to use some results of the exercises that were in the notes. I think it's rather old. In theory, people knew it in the 90s. I'm quite sure, maybe even earlier. Yes. Yeah, so I'm gonna use the results of the exercises. So I hope you did the exercises. So who did the exercises? Good. All right. So okay. So well, who noticed at least that there were exercises in the notes? Okay. Who noticed that there were notes? All right. So yeah. So I'm gonna give you the solutions to some of the exercises. Actually, I had trouble doing them myself yesterday, so I realized them, and perhaps they were a little bit difficult. So now we are going to specialize to the following thing. So of course my motivation is this inhomogeneous problem, but to explain the standard tricks, let me go back to a homogeneous problem. So let me go back to the ground state. So the ground state of some critical Hamiltonian in one dimension on an infinite line, for instance, this XX model on an infinite line. And I'm interested in the entanglement entropy of an interval A, so all the spins that live in a certain interval A, in a larger system, infinite one, say. So recall that in the other lectures I explained that typically ground state correlation functions can be obtained by imagining that we start from some just any arbitrary state S here, which we evolve in imaginary time. Let me call this tau. So which we evolve. So we take a state of our system, we evolve up in imaginary time, and after we have evolved, if we evolve for long enough, then this projects onto the ground state. So this projects onto the ground state up to some normalization that we have to take care of, and then we can insert correlation operators here if we are interested in calculating some correlation function 01, 02, 03, say, in the ground state. And then you evolve again to here. And so by applying this trick, which I'm not going to discuss in detail today, but okay, so which we discussed last time. Sorry, this is not the ground state, this is some state S, and this takes care of the normalization. So this, if you take the limit tau goes to infinity, this gives you the ground state correlation. And so by applying this trick in field theory, you end up calculating correlation functions in the plane. So correlation functions in the ground state of your quantum critical system are obtained by looking at the free boson CFT, if you want. Or other CFTs if you are in other universality classes in the plane. Okay, so that's what we are going to do. We are going to calculate a certain correlation function in the plane. Let me keep this. Yes, so the only difference with last time is that now we have to calculate correlation function not in a single system, but in a system with several copies. And so instead of having a single plane, if you want, where we would insert our operators here and here, we have now alpha different planes that are on top of each other. I'm gonna draw my pictures with alpha equals 3, but you can do this for any alpha if you want. And yes, so now that represents here the state, so the ground state for the first sheet, first plane. Then there's a second ground state and a third ground state. So 3 copies of the ground state that I get by taking some state at infinity and evolving in imaginary time. Same thing in the other direction here. And so that allows me now to calculate correlation functions in this system with copies, with different copies. And what I need to calculate, according to what we discussed here, is the expectation value of the swap operator. So this is direction x, this is imaginary time. So this is A, this is B. And I need to apply the swap operator here. Yes? Mm-hmm. So I'm going to come back to this later, but for now I just want to, I need to explain you the tricks that are involved in the calculation of entanglement entropies in conformal field theory, and to do that I want to focus on this simpler setup. So ground state on in an infinite system, and I want to calculate the entanglement entropy of an interval. I'm doing an interval because I cannot do half and right, because this would be infinite. So this is kind of the simplest case. Yeah. So I just want to explain you the technique at this point. And then once we have the technique, we will adapt it to deal with this case here. Yes. So that. Okay. So is this clear at this point? And now you have to think a bit about what this does, what this swap operator does. And what it does is that because you see it shifts the different copies. In fact, what happens is that now, so the copy 1. So when you go from here to the other side here, you go from copy, you see that you go from the copy 1 to the copy 2. So as you turn around this point here, you actually go from the first plane to the second one, and then to the second one from the second one to the third, and then from the third to the first plane again. So this is like, so if you turn around here, you always stay on the same level, on the same plane. But if you go between those 2 points here, that are the positions of the cut between A and B, if you turn around those 2 points, then you can go from one plane to the other. So if you want, this is like a sort of a parking lot, where you have you're driving your car here, and if you turn around the whole thing, then you always stay on the same level. But if you go, there are 2 pillars, say, and if you go between the 2 pillars, then you go to the other floor. So actually yesterday night I was looking for apparently. So apparently, yeah. Yeah, but this is they have not realized that it's actually useful. Is it working? So you see, I mean, this is one sheet, so one plane, and if you're driving your car, and if these are the two pillars, so this is A, this is B, and so if you go around a pillar, then you go to the other floor. But if you drive around here, then you stay on the same floor. So this is exactly this geometry, except that it's periodic. So the last the top floor is identified with the ground floor. This is what it is. And so what's important is that now we are going to say that, in fact, the correct way to look at this is to say that we have really a system that is made of alpha different copies, that it's a single system with a symmetry between all the copies, and that we have an operator here that creates a topological defect that changes the sort of the boundary condition that you pick when as you turn around the pillar here. Okay. So in other words, we are going to replace the expectation value of these alpha replicas of the ground state, of the swap operator in the alpha replicas of the ground state by a correlation function, a two-point correlation functions of the two topological defects in the field theory that is replicated alpha times. So this is in the conformal field theory replicated alpha times. And this phi, okay, so now let's now let's give some names to these two positions. What notation do I want to use? Okay, let's just say that this one is at 0. So this one is at x equals 0, and this one is at x equals LA. So the interval A is the interval 0 LA, and A union B is the real axis. So then this operator here is at 0, and this operator here is at x equals 0 and imaginary times 0, and this one is at LA and imaginary times 0. Okay? So note that I'm not doing any calculation, I'm just talking. And this is often the case actually in CFD. It's actually usually in CFD you don't have to calculate very hard. It's more about trying to find the right object that you should calculate, but then once you have correctly identified the object, the result sort of follows for free. And this is what's going to happen here. Because once we have identified, okay, so where are we now? So now we have identified this sum of the coefficient lambda I to the alpha as this. This is where we are now, okay? And so in particular, the Rényi entropy now is 1 over 1 minus alpha log of this two-point function. Okay? And now at this point, basically, we almost have the result because it's a two-point function in the plane. And so because of scale invariance, this has to go as LA, simply LA, that's the only scale that we have here. So LA to some power. And the power has to be, so this here now has to go as LA to minus 2 delta, where delta is the scaling dimension of the operator phi. And so this gives us, as a result, that the Rayleigh entropy goes as log L with a prefactor related to the scaling dimension of this operator phi. Okay? So the only thing we need, yes? Good question. Well, I would argue as follows. So I would say that I would give an argument like something along these lines. So imagine you pick an operator phi that has some scaling dimension, and let's say it's so there. In general, there is not only one operator phi that does this. There will be infinitely many that have this property that they insert that. Infinitely many that can do this, because if you have an operator phi like this, then you can bring other operators in the theory that do not create defects close to this one and create new new operators. So let's say we have one of them, and let's say it's the one with the smallest scaling dimension, smallest possible scaling dimension. Then you can, okay, so then if you write the OPE, you can actually see that it has to be a primary field, because otherwise there would be another operator with a smaller scaling dimension. So if you pick the one that has the smallest scaling dimension, it has to be primary. But this is basically like saying that in the field theory, either operators are primary or not primary, and but if they're not primary, you can always find they have to be descendants of a primary one, and so either this one is a primary or a descendant, and if it is a descendant, then I can identify the correct primary. So anyway, but yeah. Okay, perhaps super convincing, but in the end, it's a topological defect. It has to be. It's local in the sense that it inserts it's a twist field, right? So it inserts. It's the endpoint of a certain string. The string itself is not local, but it's topological. Okay. Yes. On the lattice? No, that's so on the lattice. This operator is perfectly well defined, and then this phi, I would just say, this phi would be the operator that creates the endpoint of an operator like this. I mean, if you want, it's like you can think perhaps about a Jordan-Wigner string, which is perhaps a more familiar topological object, and then this point here would be the endpoint of the Jordan-Wigner string. So it would be kind of a fermion, if you want. Well, a fermion creates a defect in the sense that if you pick another fermion and turn it around, then. No, and it's just an analogy. It wouldn't do that. This is just a more complicated version of a topological defect. I'm saying this is well defined, and then this is not really well defined. It's just the end point of this. So what is SA in terms of the fermion? SA is nothing in terms of the fermions. I was just trying to use an analogy with a Jordan-Wigner string. But if you sorry, forget about this. Maybe it was confusing. SA on the lattice is this. It's you have two. Okay, take alpha equals 2. Then you have two spin chains. Okay, sorry, I have to put them in front of one another. And SA is, let's say this is A, this is B. And SA is the operator that exchanges those two. Okay? And then phi would be just the endpoint of this SA. So I would just say that I insert phi here. It starts as a string that is going to flip to exchange my two systems. And then I put another phi, and that's just the endpoint of the swap. But phi is not really, I mean, the object that is well defined is S. Phi is just okay? But in the field theory, it's well defined as a twist operator, so something that inserts a string. Okay, are you completely confused, or? I still haven't calculated anything. First model, which? To this one? Well, I'm just assuming that the large scale correlation functions of evaluated in this microscopic model are represented at long distances by some CFT. Which, I mean, if you want, you can think more concretely about one of the spin chains that Thierry was talking about, and then the CFT is the free boson. Yeah, it has to be critical. Yes? Sorry? I take it, okay, what I'm saying is that there might be several phis in the theory that do this. I'm picking the one with the lowest possible scaling dimension. I'm picking the one with the scaling dimension, the lowest possible scaling dimension, which does this. There's only one smallest possible scaling dimension. No, because this is like no. Okay, so this is just saying that if you have one operator in your microscopic model, generically you can write it as a sum, some infinite sum of operators in the field theory with some coefficients, which depend on this operator O and on all the fields in the field theory. And I can organize this sum from lower scaling dimension to larger scaling dimension. The lower scaling dimension is going to be the one that contributes most at large distances, and all the other ones are going to generate corrections, but they won't give me the leading asymptotic behavior. Now, typically any operator that has the correct charge, or so the correct in that case the correct topological properties would typically appear here. And so I said there could be infinitely many of those, so they would all appear in this sum, but in the end, the one that will fix the asymptotic behavior will be the one with the lowest possible scaling dimension. And this is the one we are interested in. And for this one, the scaling dimension is well defined, and this is what I want to show you how to calculate it now. But why would it be 0? Okay, so then it's not 0. I mean, this is just a general principle, right? If there's not a good reason for it to be 0, then it's not 0. If it is 0, then it's because of some symmetry or something, and there. Yeah, so Andrea, you created quite a lot of confusion with your question. So let's forget about all these discussions, and yeah, so let's just say that there is one operator that does this, and now we want to know its scaling dimension. Okay, so what is important at this point is that you understand that in the end, the Renyi entropy is just expressed as some expectation value of this twist operator that changes the boundary condition, if you want, as you turn around it, and that connects the different copies. So how to fix delta, so the scaling dimension delta. So this was one of the exercises in the notes. And okay, so once you have arrived at this conclusion here, that it's a 2-point function of some operator that inserts a defect, then there are 1,000 different ways of getting the result. And let me just present one way. So it's all about, it's always, you have to play with some conformal transformation and see that the central charge pops out. So let me give you one possible derivation, and so it's going to be quite simple, but I need to use a result, a result that is really important. So use this key result, which was actually briefly mentioned by Thierry also. So it's that in a different form, but it was the same thing. So if I take my CFT on a long cylinder, long tube like this, so I have now my CFT that is living, the degrees of freedom are living on a cylinder with length L and circumference capital L, say. And I calculate the partition function of that thing. Okay, so what this means is that I calculate, so the path integral, let's say we are now again in the free boson CFT, so I calculate the path integral with my action, that I wrote as this, and now with two coordinates, say this is coordinate x, this is coordinate y. We are going to call z x plus iy. So this is integral from x equals 0 to L with periodic boundary conditions for x, and from minus L over 2, say, to L over 2 on y, and then we have the gradient of h squared. Okay, so this would be the partition function. So you take your field with the appropriate boundary conditions, and then you integrate. You take the path integral, which you have, of course, to properly regularize and everything. But so then there's a Anyway, so the partition function in the CFT contribution to the partition function goes as follows. So this goes as exponential pi c over 6 L times L, where c is the central charge. C is the central charge. And for the free boson that we've discussed, or so for Lottinger liquid, C equals 1. So if you don't like C, because you don't understand what it is, then you can just put C equals 1. Okay? So this is valid asymptotically when L is much larger than L. So when it's a very, very long cylinder. This is also what gives, so Thierry mentioned the finite size corrections to the ground state energy, and he said also that the Lottinger liquid velocity was appearing here, and the central charge, and this is the formula he was referring to. All right. So now that we have this, we can. I will just assume this. If I have time, I can explain you later where it comes from. But assuming this fundamental result in conformal field theory, I claim that now we can get the scaling dimension of this operator very easily. Any questions? Yes? No, it does not. You're this one does not contain the correction to the ground state energy does not contain the Lottinger parameter. The Lottinger parameter appears in the when you look at the spectrum of the first few when you look at the first few excited states. If you just have access to the ground state energy, you can't get the Lottinger parameter. Yes. Unless you're able to play with twist boundary conditions or do something like that. But if you really have access only to the ground state with simplest boundary conditions, then you don't see the Lottinger parameter. All right, so now we have this key result, and we just need to play with a simple conformal transformation, and we will get the result. Notice that I still haven't calculated anything. So now I will finally calculate something. So in the end, the problem is this. So we have these alpha copies. We have this twist fields, phi and phi at some position W1, say. So W1 I will later take to, so W is x plus iy. I will later take W to the origin. But for now, let me just assume that it's not at the origin. So the origin, let's say, is somewhere here. And phi of W2. So now I'm going to use the conformal map from the cylinder to the plane. which you can check reads as this. So what this does is that it takes a point on the cylinder, this is a point on the cylinder, where z is, sorry, z is x plus iy on the cylinder, y is the periodic coordinate, and this goes to the plane like this. That takes a point z, maps it to a point w. Okay, and so now we calculate. So now we use the answer to we use Andrea's question. So the phi is local, and it transforms like a primary operator, and so we are allowed to write this. On the cylinder. And now, okay, so what I'm going to do, so the z then is, so z is L over 2 pi I log W. So let me take W1 and W2 on the real axis, because this is what we want in the end. And let me take W1 quite close to the origin. So not at the origin, but close to the origin. So then you see that, okay, so if W is close to 0, then this this goes to minus infinity, and so the point Z1 that corresponds to my point W1 here is going to be very high up, so on the cylinder. Similarly, if the point W2, as I move the point W2 to the right, the point Z2 here, Z2, which lives on the cylinder, is going to be at the bottom here. And so in the end, what we need to calculate is a correlation function on the cylinder with these two on the cylinder replicated alpha times, because we still have the alpha replicas, but we have these twist fields that change the boundary conditions around the periodic direction of the cylinder. So let me write here. Okay, I'm gonna just finish the argument and then I will stop. Okay, so it's a correlation function, and a correlation function you can always write as a ratio of partition function. Yes, on the cylinder. So this is a ratio of the partition function of my cylinder replicated alpha. Okay, so let me write the denominator first. So this is the cylinder replicated alpha times. Okay, so there are there are alpha cylinders here. So one inside another, if you want, and they all have the same circumference L and the same length L. Okay? And here, because I'm inserting now because I'm inserting one of these fields phi that change the boundary condition, at some position, let's say they are at minus L over 2 and L over 2, where L over 2 is, because Z is given by this, so then you can see that L is just L over L is L over 2 pi log of, okay, this is important, so log of W2 divided by W1. Okay, so this is the positions of the 2 points, the distance between the 2 points, Z1 and Z2, after we have done this mapping. And this change, and now we have this 2 operators phi, but these phi's change the boundary condition, because they connect the different replicas as we go around them. And so now we don't have alpha different cylinders. We have a single cylinder, but it's so it's like a carpet that has been rolled, if you want. You roll it so that in total you see. I mean, okay. So if you look at it from the side, in the denominator we have something like this, while in the numerator we have something like that. Okay, where this point in the end is identified with this one, because the boundary has been condition has changed because of this field phi. Okay. And now you see that, so in the end, what we have in the denominator is just alpha times the partition function of a single cylinder, because they don't talk to each other. So this is just the partition function of a single cylinder to the alpha. While in the numerator, we have the partition function of a single cylinder, but of total circumference alpha times L. Okay? So this is what we get in the end. It's the ratio of 2 partition functions of a long cylinder whose length is given by this log of the size of the initial interval. One cylinder has circumference alpha times L, the other one has circumference L, but we have to take it alpha times. Okay, and then we use this key result, fundamental result of CFT, that this is just given by that this has this asymptotic behavior over there. And so in the end we arrive at okay, so you just have to do carefully the Jacobians. It's very easy for this conformal transformation, and so this in the end is exponential pi over 6L alpha divided by exponential pi c, sorry, let me neglect the c, pi to the alpha. Okay, and L is this now, and so this is in the end I can replace by so this is W1 delta, W2 delta, and here W2 over W1 to the power 1 over 12. Okay, so to some power okay, let me call it delta prime, and delta prime is just 1 over 12 alpha minus delta prime, and so this is alpha minus 1 over alpha. Okay, and now you see that if you bring this to the origin, nothing special should happen in the plane, because it's just a convention. So this shouldn't have anything special when W1 goes to 0. But in this result, as it is written here, something special happens, unless delta is delta prime. In that case, the two terms cancel. And so we see that delta has to be equal to this. This has to be this delta. This has to be the scaling dimension of the field, and so we end up with this. And so this, in the end, is just as it should. It's just 1 over del 2 W2 basically to the 2 delta when W1 goes to 0. And so that's it. So we have the scaling dimension, we have it now everything, and so when we plug this here, we end up with S alpha equals 1 over 6. Okay. Alpha minus 1 over alpha divided by 1 minus alpha log of system size LA. And you can simplify this, and this gives 1 plus 1 over alpha. Okay, so this is the CFT calculation of entanglement entropies. And in the second hour, I'm going to just, it will be less technical. I will be just applying this to this quench. Again, without calculating much, it will be just about identifying the right thing to calculate. Okay, that's it. Thanks. Yes. All right. So, okay. So now I told you how to calculate entanglement entropy. So it's basically playing around with these twist operators. Yeah. So in the argument I used, I relied on this sort of fundamental result. And I was planning to explain this a little bit, but I guess I'm gonna have to skip it. I mean, unless someone is really eager to hear about Schwarzian derivatives. So, who wants to hear about Schwarzian derivatives? I mean, they're nice, but no, it's really not a nice derivation. But yeah, okay. Let me talk about the initial problem I wanted to talk about, and then if I have time in the end, I'll tell you more about Schwarzian derivatives. Okay, so now I forget about my homogeneous critical quantum spin chain, I just keep in mind that I now know how to calculate entanglement entropies. And I come back to the initial problem, which was this one. So a particular case of the problem that was discussed by Bruno. Okay, so the first thing we need to do is calculate the density profile. So now I want to, okay, so generalized, generalized hydrodynamics, which was, okay, but I mean this is really an overkill here because it's just going to be a free problem. So, but yeah, just to make the connection with the bonus lecture of the domain will quench. And you will see that in that case, it's, I mean, it's particularly easy. So, okay, so the Hamiltonian of the XX chain here can be diagonalized by going to Fourier space. So, in Fourier space, this is this, where epsilon of k is minus cosine k. And so this tells us that we have particles, so fermions, moving, free fermions moving at their group velocity v of k, which is the derivative of epsilon with respect to k, sine, which is just sine k. And so we can adopt the following semi-classical picture. So we can say, let's look at an object, which I'm going to call W, of x, k, and t, which is the which is semi-classically the probability of having a particle, a fermion, a particle at position x, and momentum k in my system at time t. And so because the particles are free, then what's going to happen is the following. So I can picture my initial state as this. So initially, so this is now phase space. This is x, this is k. K goes from minus pi to pi. This is important. This integral here is from minus pi to pi. The Brillouin zone is compact, so I have periodic boundary conditions here. So this is same as this is periodic here, so it's like a cylinder. And so initially, since the system is completely filled on the left, there are particles everywhere on the left. My function w here has to be 1 on this side, because so the probability of having particles on this side is just 1. and the probability of having particles on the other side is 0. But now, since these behave as free particles, then I can just take, if I have a particle that is here, say, that has initially a position x and momentum k, then because it has momentum k, it has to be moving at velocity sine k, or vk, and so after time t, I will find it at this position, which is going to be x plus v of k times t. Okay? So in other words, this function w has to satisfy the following equation. So w at time t is related to w at time 0 by this, in this way. Okay. And so this just means that after time t, I will have the following picture because the velocity, if a sine of k, this is k, so I have to plot the function sine of k, which looks like this. Okay. So this means that now w is going to be 1 on this side and w is going to be 0 on that side. Okay, so this is the phase space occupation after time t in this semi-classical picture. And so now I can get the density profile for free because I just need to say that so the density at position x and time t, which is which in the original microscopic model is defined as this. So it's the expectation value of c dagger x cx e minus I h t psi naught. So this is in this picture, semi-classical picture, it has to be given by this. So in other words, I just, if I want to know the density at a given position here, let's say here, I need to integrate W along the vertical axis at this position. Sorry? Yeah, so W is the Wigner function, yes, thank you. Then I don't understand. I don't know what that means. Hmm? Ah, okay. Yes. All right, and so then because we have this here, and because v is just sine k, then you can see that this is 1 over pi arc cosine x over t. At the leading order. Of course, there are, as Bruno discussed in the last lecture, this is only true in this hydrodynamic limit. So if you wait for long enough, so that locally you have this fluid cells and so on, and so there are corrections. But in the limit t goes to infinity, which is the limit that Bruno was discussing. So t goes to infinity and x over t fixed. This is exact. Okay, so that's very simple. And so let me just emphasize something here, which is that this is, of course, very simple, and that was known a long time ago. But I think for a very long time it was really a huge challenge to go to the interacting case, and really no one had a clue how to do this, and so Bruno and co-authors did that, and that was really amazing. So now, basically, this simple picture here, it also exists for the interacting case, which is quite amazing, I think. And actually, Andrea and Mario Colura and Jacopo Vitti, so they solved this case in the interacting case. They solved this problem for XXZ, which like 2 years ago, right? And I mean, 4 or 5 years ago, it was really a dream, right? It was completely out of reach. But thanks to generalized hydrodynamics, you can now do this for the interacting case. Okay. Good. So now what does this have to do with CFT? So at this point, it doesn't have much to do. But now we want, in the spirit of what I've been discussing on Monday and Wednesday, we would like to look at quantum fluctuations around this classical solution. Let me erase this. And okay, so it's probably possible to do this in a more direct way than what I'm going to tell you. But at the moment, I'm not sure how to do it in a more direct way, so I'm going to discuss it in the way we wrote it in the paper 2 years ago. But yeah, this is probably not very optimal, but anyway. It allows to make a cool connection with a different topic, of which Filippo is the world expert. So I will quickly discuss this now. So let's go to imaginary time. So when one does field theory, it's often a useful trick to go to imaginary time. So in principle, we're interested in. In principle, we are interested in real-time observables. So, in principle, we are interested in calculating things like this. So, in that initial state, e to the IHT, some observable at position x and e to the minus IHT. But what I'm going to do instead is that I'm going to calculate some observable at time tau. There will be some parameter r at imaginary time tau, and that what this means is that we are going to calculate something like that. So notice that there is no I anymore. So we are going to calculate something like that by mapping the problem to some classical statistical mechanics problem in 2 dimensions. And then at the end, so at the very end of the calculation, we will take tau to IT, so that this becomes this, and then R to 0, or maybe not R to 0, but tau much larger than R. And t much larger than R, and x over t fixed. But when we work in imaginary time tau has to be between R and minus R. Okay, and so what's the picture for this? So the picture is the following. So we have our initial state, which is filled with particles here on the left, empty on the right. Then we evolve it in imaginary time. And so we insert some observable here at time. This is, okay, so my axes now are like this. So this is x, this is tau. This is tau equals minus R. This is tau equals plus R. And imagine that I want to calculate the expectation value of some observable that is here at x and tau. So I have, again, this is the state that is completely filled and empty on the right. And so the question is, how does this connect to conformal field theory? Because, okay, now we have really a spin chain, and we have to imagine that the particles here move in imaginary time, but you see this is very constrained. These are fermions, so they cannot hop left or right, because the left and right are neighboring sites are fully occupied. So basically, far on the left here, the only thing that can happen is that this fermion just goes there, and because it's so much constrained that it can't move. So yeah, so the problem is too constrained on the left, so to have any degrees of freedom. And the same thing happens on the right. So here there is nothing, here there is nothing either. However, here the particles can start hopping, and so here in the middle there's a region that is going to grow, and that's going to have some shape that's going to look like that, in which the density, so that here the density is neither 0 nor 1. Okay, so here the density has to be 1, here the density has to be 0, and so in some region of the middle, in the middle, it's neither 0 nor 1. Is that okay? And so you see there can be fluctuations. So there can be interesting fluctuations only in the region where rho is not 1 or not 0, because this is just the vacuum. This means just that locally, if you cut a small piece here, it's going to look like the vacuum, and the vacuum has there's nothing interesting to say about the vacuum. Same thing here. Here this will just be a completely filled state, not interesting to say, but here there will be fluctuations. Yes? Because this is what I'm going to take, the limit I'm going to take in the end, so that I put IT here. So then it looks a bit more than like that, but I also want to take R to 0, if you want, so that it's really like that. I wanted to say exactly what I have to do if I know this quantity to recover that one. Yes, so that's the miracle of analytic continuations. You calculate something for tau real with this constraint, then you take tau to, you'd say, now I take tau imaginary, and then you forget about the constraint, you write something, and in the end, if you get a meaningful result, then you say, aha, this is the proof. Okay, so let me now connect to. So this kind of problems is quite well known in the literature. Again, Filippo is really the world expert, and so it's known as Arctic Circle types of problems. So. So what this model here, this picture is here is just a square lattice paved with dimers or dominoes. Notice that okay, so it's yeah, okay, so it's a okay, I'm not gonna try to draw it, but I mean, you see what it is, right? So it's really just a domino tiling of the square lattice, and it's just that you have to choose the orientation of the lattice in a slightly it's rotated by 45 degrees, so that the boundary condition becomes slightly non-trivial for the dominoes, and what happens, it's really here a uniform distribution of all possible configurations, no constraint at the boundary or anything. And what happens is just that as you grow the system, you have a sort of a shape that emerges in the middle. So the dominoes spontaneously freeze in the corners, and you have a region that emerges in the middle with fluctuations. And if you, so this is for a not so big picture. If you do a larger picture, it looks like this. So you really have an emergent shape, which for dominoes is just, for this problem, is just a circle. So there are other examples that you can find on the web. So this is, for instance, a losange tiling. So it's on the honeycomb lattice. And I'm showing you this picture because it connects to what I'm discussing here. So if you look at this as a trajectory, if you look at the yellow and pink losanges, you can view those as trajectory particles if you want. So with the rule that if you go, imagine that you have a particle here, then I make it hop to the top of the losange and to the top of this one, to the top of this one, to the top of that one, and so on. So this gives you a trajectory of a particle. This also gives you a trajectory of a particle. This also gives you another trajectory, and so on. You see that because of the boundary condition which is imposed, which is that all the losanges here are pink on that half of the system, and that they are blue on that half of the system. So because of that constraint, far on the left, nothing can happen. This is automatically the only configurations that you can get. Similarly on the right. But in the middle, your particle can start having different trajectories. And so this is really very close to this problem that we have in mind now. And actually, as you take the thermodynamic limit, there is also one of these limit shapes that emerges. Okay. And so this is what happens in our problem now here. So it's really analogous to the previous situation. It's just that now we are doing this in continuous time, because we have a Hamiltonian, not a transfer matrix. So it's continuous time, but otherwise it's quite similar. And so what happens is that the density has to be 1 on the left, 0 on the right, and in a certain region in the middle, which happens to be just a disk, the density is neither 0 nor 1. And so this is the region where I can have interesting fluctuations described by conformal field theory and so on. And this is what I'm going to use. So the density of particles at position x and t can be calculated, and the result is this. Okay, so notice that it looks very close to this. Sorry, this is tau. So it looks very close to this, and indeed if you take tau to it, and then take it much larger than r, then you recover that. Okay, so it's kind of consistent. Yes? XX, it's the XX chain. Yeah. Mm-hmm. Okay, and now, okay, so I won't enter any technical details here, but it turns out that the fluctuations inside this shape here are given by, again, a Gaussian free field in a certain metric, because the system again is not homogeneous, so you shouldn't expect that the effective field theory that describes the fluctuations would be translation invariant or anything. Okay, let me erase this. So, okay, so it turns out, and I'm not going to show this, but it turns out, so the fluctuations, inside the Arctic Circle, so inside that region here. So again, this is rho equals 1, rho equals 0, and here we have some interesting density profile. So the fluctuations inside that region are captured by a Gaussian free field, by the GFF, at some value of k. So just to check that you're following, so what's the value of k? Yes, because it's free fermions, so it has to be 1. It's the underlying microscopic model is free fermions, so it has to be 1. And yeah, so in a certain metric, I mean, okay, I can write the metric for you. It's this. Mm-hmm. And so basically this is all we need to know, because now we know the underlying geometry of the problem. We know how to we know what exactly the field theory is. Therefore we know how to calculate correlation functions. and that's all what's needed. So of course now, since we are interested in the entanglement entropy, what we really have to do, let me erase this, what we really need to do is take several copies of the system and insert the swap operator, but this doesn't change much, because now we can imagine that we have so different copies. We have this circle in the middle, so we have copies like this. Each of those has an Arctic circle, and then we just have to insert the swap operator. So the initial problem was to calculate the entanglement entropy. So the density profile after time t looks something like this. I said it's an arc cosine, so it looks like this. This is rho of x and t at time t, and this is x. This is minus t, and this is t, because the maximal velocity is 1 in this problem. And I said we were interested in calculating the entanglement entropy at position x, so this is A and this is B. Semi-infinite system, left and right. And so what we need to do is insert the swap operator here. So the swap operator is coming from infinity. It acts and it shifts again. It shifts the different copies here. This is the pillar, if you want. So this is the parking lot again. This is the pillar, and the other pillar is at infinity. So if you're in your car and you turn around here, you go to the other level. And yes, and again in field theory, this is just some operator phi, and we need to. So what we end up with is the expectation value of an operator phi inserted inside this Arctic circle. The other operator phi is at infinity. Okay? And so now with the technology I presented in the first lecture, which was really started by Pasquale and John Cardy and developed by many other people like Eric and many others. So you just need to calculate a one-point function inside that funny geometry. Since we know the metric and everything, this is easy to do. So let me just give you the result. I mean, if you really want the details, it's a 3-line calculation. So it's really not complicated once you know everything. So again, in this type of problems, what's really important is to correctly identify what you need to calculate. But once it's identified, the calculation itself is usually elementary. And so, okay, so this is the result in the end. In imaginary time, and then you take tau to it, and as I said, then a t much larger than r, with x over t fixed. And this gives the result in the form that I had presented in the beginning, so it gives this. So I think that's it. That's basically what I wanted to say. Now, should I talk about Schwarzian derivatives? Okay, maybe not. Maybe not. If you want to, if you want me to talk about Schwarzian derivatives, I can do that in private, maybe. Uh, okay, so it's because, yeah, thanks, sorry. I should have said this. Okay, so you need to find a nicer system of a nicer coordinate system just to get rid of the to work in flat metric. So imagine that we have some function xz of x and y that is not just x plus iy in this case, but something more complicated. So I have it here. I can give it to you. It's here. Okay, so yeah, so this is not x plus iy. What it is in that particular problem is arc cosine x root r squared minus y squared minus I arc tangent hyperbolic. Okay, well, it turns out to be that. And then in those coordinates, you can write this as the metric becomes just dz bar, so it's the Euclidean metric times some conformal factor, and this sorry. Arc I'm not sure what arctangent hyperbolic arctangent, yes. And this sigma here is a function of x and tau, or z and z bar if you prefer. This is just a nicer coordinate system, because in this coordinate system the metric is now takes this conformal form. It turns out the coordinate z here is, you see, z, the imaginary part of z goes from 0 to pi, and the okay, so this is ds2. So this is now z of x and y. So the real part of z goes from 0 to pi, and the imaginary part of z goes from minus infinity to infinity. Okay, so we are parameterizing points inside the disk by points on this strip. So we end up with our favorite geometry, which is the infinite strip. And then we just need to calculate a one-point function in the strip, and that I told you how to do last week. And the only thing we need to keep track of is this factor here, but the dependence on this factor is kind of trivial. It's just that, so yeah, we end up calculating this here in the strip. No, let me write it as this. So this is in the circle. So in the original problem with this metric that I wrote, and this is just it's this one-point function in the strip with a Euclidean metric. So this is really what I told you how to calculate last week. And then there's just a Jacobian. You pick up the Jacobian of this change of coordinates, which happens to be this conformal factor here. So you get a e to the minus sigma cz bar to the delta, where delta is the scaling dimension of phi. Yeah, so it's again just the transformation law of primary operators. Mm-hmm. Okay, well, so if there are no other questions, then that's it. Uh-huh. Mm-hmm. Yes. Yes. I mean, you can calculate the entropies numerically, and yeah, and clearly this is the correct result even for alpha different from not integer, but of course there's no, at least in the way I explained it, there's no good reason why it should be correct even for alpha non-integer. But in fact, I think there is a much better reason, because since in the end it's just about playing with these geometries with cones, because basically these twist operators, they're just they're locally changing the geometry, so that in fact you are playing with a cone that has an angle 2 pi times alpha. But the angle of a cone is not something that has to be an integer times 2 pi. It can be just any continuous number. And so from that point of view, it's kind of clear that it should depend continuously on the angle. But maybe Eric has more to say about this. So, okay, so in the end, when we use the replica trick, it's all about alpha integer larger than 2. So how comes we actually get the result for any alpha?
Okay.
I mean, so what I said. Yeah, but you have a more. So I said that. What do you mean alpha is trivial? Well, in the end, you don't need it, but yes. Yes, but is there like a deeper reason for that? So I said that because alpha in the end is the angle of a cone. The angle of a cone doesn't have to be an integer times 2 pi. So you can already see at this level that it's. Yes, I know. Yeah. So, but yeah. Okay, so.
Extend alpha to a complex field to look at the imaginary axis, if it converts from impact, then the continuation is good. Practically, what we do is take the direction of alpha here, and then you check if the numerics is okay. The point is that the twist field are not defined.
Simple problem of a single interval. Then it's not related to a trace of rho a to the alpha, but geometrically it's still a well-defined object. The problem is when you have more points, right? Anyway, so maybe let's stop here. And yeah, so let me thank again the organizers. I was really happy to give these lectures, and thank you for listening.